Gabi. Hello, my name is Georgy. I work at Newcastle University with Andrei Mokhov and Jakob Lechner at RUAG Space Austria. And today I will show you how to make software engineers who write software for spacecrafts to write Haskell. And yes, so what do we want to achieve? We would like to send satellites into space. But what we do not want to have, and what sometimes happens, is to, together with those satellites, send bugs into space. So we'd like to avoid that, satellites in space with no bugs. And how are we going to do that? So we're going to look at these people in the RUAG space, they use a specialized instruction set called Redfin, which stands for Reduced Instruction Set for Fixed Point and Integer Arithmetic. And what's its purpose? Its main application is to be deployed as a part of a control unit for solar panels and antenna pointing units. And it's supposed to be a substitute for custom FPGA deployed control circuitry. So these people used to have FPGAs with 5 or 6 functions that were designed to control solar panel units or antenna pointing units, but then they decided that it would be actually great if we could reconfigure our stuff in space. So they created a small instruction set architecture that was specifically designed to do this simple, really basic control tasks. There would be a big processor, the central processor of the satellite that would execute the programs on Redfin, trigger some procedures executed on Redfin. And Redfin is a small core processor used specifically to do these simple control tasks. So that's why Redfin is really minimalistic. It's just a instructions architecture that has arithmetical instructions, conditional jumps, and importantly, it doesn't have procedures. So you can't do subprograms with it, and that's beneficial. So the code must be simple. So if a program you want to deploy to Redfin doesn't fit in, say, 200 lines of assembly, it shouldn't go to that processor. It should go to the central processor. And it has deterministic execution behavior, so it doesn't have any things like speculative execution or concurrency or anything like that, so it's completely deterministic. And deliberate small hardware footprint, so it could fit on small space-qualified FPGAs. Which has all kinds of radiation protection and stuff like that. So these design properties of Redfin supposedly make it amenable to formal verification of programs. And by verification, formal verification, I mean complete verification. So we're not doing randomized testing, we're not doing bounded model checking, we're doing complete model checking, so full verification of programs for all possible inputs. Let's take a look at a simple example. And the software engineers that program for Redfin usually write this kind of short assembly scripts. And it's not exactly clear what that program does, right? Because it's some assembly mnemonics and some registers, some memory allocations. You know, it could do anything. But in fact, it just computes this simple arithmetic function. So it takes 2 time points, T1 and T2, 2 power values, P1 and P2. It adds up the power values and multiplies by the absolute difference of 2 time points, divides by 2, and takes the floor. We know how to encode that in Haskell probably. That should be really simple. And the space engineers know how to write that in assembly. And we know how to work with Haskell. We know how to make Haskell secure and safe and stuff like that. So we need to transfer that somehow to the assembly and make a tool for spacecraft software engineers to write their programs in assembly. So we make them to write Haskell by embedding assembly into Haskell in that way, really seamlessly. So our assembly mnemonics just become regular Haskell functions, and we've got this nice type signature that says it's an assembly script, and we can even employ some additional syntactic instructions like let bindings and seamlessly embed assembly as an embedded DSL into Haskell. So what we would like to prove for that program now? We would like to prove that for every possible value of the input parameters, the time points and the power values, integer overflow doesn't get triggered, meaning that at any point in the program, there wasn't a possibility for integer overflow to happen. And we formulate that in the following way. So we say that for every possible value of the input parameters, the final state of the overflow flag is 0. So this final state of the overflow flag is a summary of all the states that this flag took during the program execution. And in our framework, we just formulate it like that. So we say, dear framework, please symbolically simulate my program, taking some initial state, and extract the final value of the overflow flag and symbolically compare it to 0. And then pass it to Z3 and ask it to verify it. And so in about 4 seconds on that very laptop, Z3 gives us a counterexample for that property. Because we didn't in any way constrain the input variables, it found the assignment of the variables here, which could possibly cause an integer overflow. So if we substitute those concrete values into the program, we will get an integer overflow. So right. So how did that work? What was the semantics of all that? So we started with assembly, and we somehow compiled it into a sequence of what we call state transformers, basically symbolic computations in the state monad. I will explain that later. And so that semantics got compiled into SMT formulas, a sequence of SMT statements that is something that SMT solvers can understand. And together with some specification, that theorem we have formulated, that got fed into that 3, and it gave us an answer for our question. But with our framework, we can actually do more than that. So besides just writing assembly, we can actually write high-level specifications for our programs in Haskell, in a subset of Haskell. And we can refine this specification with efficient implementations in assembly. And by doing symbolic execution of both the specification and the assembly implementation, we can do equivalence proof that the efficient assembly specification refines the simple and concise Haskell specification. And we can also generate code to be executed at the real hardware, but that's just simple code generation problem. Nothing too difficult happens here. Right, so let's take a look at the equivalence example. So we would like to take this basic energy estimation formula and transfer it down to Haskell in this straightforward way. So we just take the values, sum them up, multiply by the absolute difference of the time points, and divide by 2. So here we have the same program we've seen before, which is basically the assembly translation of that formula. And we would like to prove that for every time point and for every power value, the semantics of that programs are actually equivalent. So the specification and the refined implementation do the same thing. So we can do that with symbolic execution. But now we would like to, so I will show you the syntax that's used. And I'm using a Haskell library called SBV, which is a generic Haskell library for basically symbolically executing almost any Haskell code. And it's very useful. Right. So we formulate our equivalence as this kind of theorem. So we return a symbolic Boolean. And first we universally quantify over the 4 values we have, so the 2 time points and the 2 power values. So I'm using this fancy Haskell notation in order to avoid writing this line 4 times. So I'm just saying that I would like to take 4 symbolic integer values and call them T1, T2, P1, and P2. And now, I would like to constrain these values one by one to be in range from 0. So for the time points to be in range from 0 to 30 years in milliseconds. So here I'm using special special types to implement domain-specific unit types, units of measurement types. So I would like to constrain my input values to be in the mission-specific ranges. Having those values constrained, I now initialize the memory. So I create the initial state of the memory. So I put T1 in the memory location 0, T2 in the memory location 1, and so on, and some service values that I don't really need to explain here. And so then I simulate my program for 100 steps, providing some kind of a initial state. I mean, the initial state of the memory, and I extract the result of both low-level and high-level programs. And now, having those symbolic execution performed, I can compare the results of both high-level and low-level programs and formulate the property I would like to prove, that for every input value, the behavior, so the function, the high-level and the low-level programs are actually functional equivalent. And I can again use T3 to prove that for me. And in about 10 seconds, I can prove that on this small laptop, because as a poor PhD student, I don't really have an access to a huge cluster. But that's all right. So these kind of properties could be proved for almost any programs that the space engineers need to write. So I would like to tell you now how to actually implement this stuff. So what things in Haskell we use to implement all that. But before that, I will tell you a bit more about how symbolic execution for assembly programs work. So during the symbolic execution, our programs branch, right? So if we have a conditional branch, we can compare for equality with this command cmp-ec the value of the register R1 and the memory location 42. And so depending on what that comparison has returned, we can perform a conditional jump. So we will offset the program counter x times if the equality was true, and will not offset it if it wasn't true. So if the values in the register and the memory location are equal, we will go and substitute the value from the value in memory location 0 from the register. Otherwise, we will add up something to it. So now we have these two possible worlds, two possible traces in our program. And there are flavors of symbolic execution that work with that. So they would split up the program on all possible traces and verify these traces one by one. But what SBV uses, and what we are forced sort of to use, but what we are using in our approach, is a special flavor of symbolic execution called symbolic execution with merging. So so now we can, after we have branched, we can actually go and merge the two possible worlds and achieve a merge state of the world. So, and the path constraints would become a disjunction of those two constraints we had on, oh, sorry, what have I done? Oh, right, on the two worlds. And the goal for that, so the goal for using symbolic execution with merging is to turn our program and the specification into a single SMT formula to achieve whole program verification. So we're not aiming at verifying some traces or verifying the possible worlds one by one, but we would like to compile the whole program down to a single SMT formula and achieve full program verification. And there is a great survey paper that analyzes and looks into different flavors of symbolic execution, written by people from Sapienza University of Rome, I believe, and that's a great paper. I encourage you to go and take a look at it. And right, so we've taken a look at symbolic execution, and now we could actually take a look at the Haskell sort of things, right? So which Haskell concepts are we using to implement the framework here? So as I said, we're embedding assembly as a domain-specific language, as an embedded domain-specific language. So actually, assembly just write a monad for us. So it goes through the goes through the sequence of instructions and writes the corresponding opcodes and instruction codes into a list, and we'll then go and execute them in our state transformer semantics, which is a state monad over the state of the processor, which is the collection of the registers, the collection of the flags, memory, and the program which has been compiled or generated from the assembly writer monad, and also importantly a system clock. So every instruction alters the state of the system clock, which we will later use to do best worst case execution time analysis, which is also quite useful for the space engineers. Right, so and for symbolic execution, we're using, as I said before, this library called SBV. It's available on HaskellX. And as I said again, I can't advertise this library enough. So you can basically take any Haskell program you have and with minor modifications, turn it into a symbolically executed program. So all you need to do is to substitute, you need to substitute your regular Haskell types like integer or strings or algebraic data types to their symbolic counterparts. But that's not that difficult, and that gives you a huge advantage. So quite alternative to other Terra improving techniques like we've seen in the previous talk. So it gives you automatic Terra improving. Right, so let's now take a look at how the semantics of instructions are really implemented in terms of those state transformers I've been talking before. So consider a really simple instruction, a simplified version of the addition instruction that extracts a value from the register 1, and the memory location adds them up. So it has data dependencies. It reads the value from the register, from the memory location, and also writes it back to the register, and also alters the state of the overflow flag. So we can automatically generate this kind of diagrams quite seamlessly from our semantics. And the Haskell implementation of that is, again, the computational red field monad, which is basically a state monad. We first need to extract the snapshot of our current state, the arguments from the registers, and from a memory location. Now we need to compute the pure value, which is the overflow condition, the symbolic overflow condition. And here, those funny operators are imported from the SBV library. So they give us symbolic counterparts to regular comparison and logical operators. So this dot greater is just a symbolic counterpart for the regular Haskell greater operator from the old type class. And this triple ampersand symbol is just the symbolic AND. So it takes two symbolic booleans and gives you back a new symbolic boolean, which is a conjunction of the two. And so we have this overflow condition now. So we know if overflow has happened or not. And we generate an overflow, right? Yes, yes, please. Oh, yes, so sorry. So this is just int 64 or int 32. So it's the type or like 64-bit word, for instance. So that's just the type of the value values my semantics operates with. So it's just the basically data path length of the processor. Right, thanks. So we need to create the possible state of the world where overflow did happen. So we generate the overflow state, altering the snapshot of the state we've taken before, with this command. So we just write overflow true into it. And the interesting thing happens in the next line. So we need to actually merge those two possible worlds, right? So we use the conditional, the symbolic conditional operator from the library, which takes the symbolic boolean and two branches. And if symbolic boolean is true, it returns the first branch, otherwise it returns the second branch. So as your usual if then else statement, but a symbolic counterpart. And here this A data type needs to be an instance of the special mergeable type class defined in the library SBB, which is not really interesting to talk about here, but it just basically tells you how to merge two symbolic values together. And so after we have merged our states, we need to alter it with the upgraded value of the register. So I hope that made a lot of sense, but feel free to ask questions. Right. So, right?
Thank you.
This condition.
So you have an overflow, and then you have an overflow state which you just generated. It's like it's unconditional in the sense.
Not exactly. So I just need, so in order to use this ITE operator here, I need to create two values of type A. So A here, in my case, is my processor state data type. So I need to get my old state and my overflow state. So if overflow happened, I would return overflow state with the overflow flag triggered. But if it did not happen, I would return the previous state. So now, after that line has been executed, I would have some state altered, some kind of altered state in my computation, and I will update that altered state, either an overflow state or the not overflow, the initial state, with the value of the sum of the two arguments.
All right.
So at that point, I'm not updating my state. I'm updating it here. So I'm merging two possible universes into one, depending on the condition of that symbolic boolean. Right. And this kind of semantics is defined for all instructions, including conditionals and other arithmetical instructions and shifts and Boolean instructions. And so this is like the generic way of defining all the instructions. So all semantics of every instructions in terms of symbolic execution is just a computation in a state monad. So you don't really need to think about symbolic computations here. So that's what SBV gives you. You can just, you can basically write a simulator, like pretend like you're writing a simulator for your processor, for your instruction set architecture. But just instead of regular Haskell functions and conditionals and stuff like that, you use symbolic counterparts. So you don't need to know that symbolic execution even is happening here. You're just writing a simulator, and then you can symbolically execute it. So that's what SBV gives you here. Right, so what more does it give you? It actually gives you a possibility to perform worst-case execution time analysis for your programs. So imagine we had a program that worked for more cycles given negative arguments, and for less cycles given positive arguments. So we can maximize and minimize the value of the system clock extracted from the final state, and get, for instance, the assignment of the input variables that is optimal for the best case, and for the worst case. So here, for the best case, we got 12 cycles, and for the worst case, we got 13 cycles. So imagine we had a conditional, for instance, conditional jump that would be sometimes executed and sometimes not. So that would give us an analysis for that. Right. So we also did a micro benchmark of our library So we wanted to know how good symbolic execution is actually working. I mean, how much time would it get to verify some examples. And so we did it on a synthetic example of summing up an array of numbers. And the important thing here is we know how much numbers we have in advance. So we do not quantify on the length of the array. So we don't have issues with symbolic termination, for instance. And you don't need to actually look inside this table. What do you need to look at is those things I've printed here. The interesting thing here is that with the linear growth of the array size, the number of SMT statements, of SMT clauses, grows linearly. So it means that the longer the array, the longer is the undivided program. So the more iterations the loop have, and I mean that's what you expect. But the verification time grows exponentially. So that is still a NP hard problem. This is SMT solving. So with symbolic execution, you can't really expect things going really fast. So you need to either have a really strong computer or invent a way of executing NP hard problems polynomially, which probably is not going to happen, right? Symbolic execution is a powerful technique, but it might be slow. Right, so we showed that to our colleagues at Ruakspace, and they thought, yeah, that's cool, but so now we would like to give you like a real example, the real control program, and we would like to take a look how you could verify that. So the example of that was, so imagine a stepper motor that controls a solar panel or an antenna pointing unit again. So in order to move a solar panel and like point it to the sun to get more energy, we need to first accelerate the motor for some time, then move it with a steady speed, and then decelerate. And it is really important that this movement happens correctly in terms of that speed is not exceeded and the acceleration is exceeded in order to not introduce any disturbances in the whole system. The plot of velocity over time would look something like that. So we will first accelerate for some time, then move with a steady speed, then decelerate, and the distance over time would look something like that. So this program is basically a big while loop with the body of around 100 assembly instructions. But the big difference, the difference that really makes sense to us is that the termination condition of that loop depends on some input values. So let's take a look at the parameters of this algorithm. So we've got 3 input parameters. We've got the distance on which the solar panel or the antenna needs to be moved. We've got the maximum velocity and the maximum acceleration. And the state of the loop would be the current distance covered, S, the current speed, V, the next value of the speed, which we would use on the next iteration, it could be either greater than V or lower than V or the same, and the acceleration. And unfortunately, since the termination of the algorithm depends on the input value, meaning distance, we can't really apply the complete verification technique, like the complete methodology we've been using before, because our execution, so like the tree I've been drawing you before would just blow up. It would just be so huge. Instead, we need to use another technique. So what we can do, we can verify a loop invariant for our loop, since our program is just a huge loop. And we can prove that for every value of the state of the loop, meaning the current speed, the current distance covered, and for all the input values, the maximum speed, the maximum acceleration, and the distance, we can prove that speed never exceeds the maximum speed. And the difference of the speed in the next speed never exceeds the, so I need V next here also, right? Sorry. The difference of the current speed and the next value of the speed never exceeds the maximum acceleration. So that would give us assurance that our program doesn't create any drastic perturbations in the whole system. And so verifying that was a bit challenging in our approach, so that was taking a bit more time than the example I've been showing you before, like about 10 minutes or 15 minutes for a constrained set of inputs. And so for real problems, you really need computational power. And you can't really verify the whole loop with the kind of naive approach we've been using. But there are techniques that can do that, and that's probably where bounded model checking comes into the picture. So instead of going all in and trying to verify the loop for like every possible value of input variables and for an unbounded amount of iterations, we can say that, for instance, for 100 iterations of the loop, everything is going to be fine, or 10,000 iterations of the loop, everything is going to be fine. But yeah, that's kind of brings us to the conclusion, so that we can, with that approach, with that specific approach, symbolic execution with merging, we can verify simple arithmetic expressions, and that's like 80% of the use cases that people at RUAC actually need. We can verify finite loops. So if we know in advance how much iterations we would require, we can verify those as whole programs in a push-button approach. And that's what the engineers want. They don't really want to do their proofs in Agda or Coq. They want to write the program in assembly and prove it. I mean, given the specification. And we can verify invariants of while loops. And that's good because the engineers need to come up with those invariants anyway, because that's the right in the specifications and documentation and stuff like that. And we can't really do inductive proofs, but SMT solving community and the automatic verification community generally kind of struggles with that. So it's expected that we can't really do that. And indirect memory access gives us problems. So if we need to load the value from a memory cell, which is referred by the value in another memory cell, it actually creates big problems for us. But that's again an unsolved issue, really, in the community. And yes, so I think that's about all I wanted to tell you. Thank you very much, and can I please have your questions?
Thank you very much, Georgy.
Thank you for your talk. Very interesting. 2 slides before, when you were checking one next. Yeah, you're just noting your acceleration. It's just a difference in 2 velocities.
Yes.
Isn't there a time component to there, or is that 1 second apart?
I mean, that's just so here everything is unitless. So that's just the way. This actually that program that does that thing was implemented by a real person sitting at that company. So I went to them and asked, so please give me an example of a program you would write. So they opened Visual Studio Code for them, set up my Haskell environment, and left them for like 2 hours, came back, and they gave me a program in assembly. And yes, that's the implementation they gave me. They used they formulated acceleration as a difference of 2 speeds, so everything is unitless. So that's just the way they did it. It's like yes, yeah, yes. I mean, does that answer your question? Yeah.
Thanks for your talk. I actually have a couple of questions, if I may. So one of them is, like, on one of the first slides, you actually had steps equals 100. And why is it like 100 steps? Why not 1,000 steps or 10,000 steps?
Oh, yes. Let me just.
I'm just got a little bit confused, since, like, when you're doing abstract interpretation, you're usually kind of loop until you reach a fixed point?
Yes. So here we do that for, that actually doesn't matter because the program is finite. So that program is actually going to take 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. 8 steps, in fact. And this is just an example value. But generally, yes. So generally, we can use it to do bounded model checking. So we're not doing abstract interpretation. So we don't do like fixed point analysis, and we're not trying to find out the loop invariance by ourselves. This is just a value. So we can do 1,000 or like 2,000 or I don't know, as much as we can afford. So right.
Probably the question is like, how do you know that enough is enough?
Yes, so you try, as Phil was saying in his keynote, so you try 1,000. If it doesn't work, you try 2,000. Then you try 10,000. And if that doesn't work, it's probably not going to work at all. But that's like, there are techniques how to avoid that. But what we are trying to do, and I'm trying to stress that out again, we're trying to create a tool with a simple interface, relatively simple interface, so people without a huge training in formal methods could use it. They're not probably going to write that. I would expect them to have some kind of configuration file, like in YAML or whatever, where they specify this sort of constraints, when they declare their variables, and where they declare the amount of steps they would like to execute their program for.
All right, makes sense. And the second one is, so writing Haskell is nice, but why do we need to embed the assembly into like Haskell DSL? Why not just parse the assembly files?
Yeah, that's a good question. So actually, I did that also. So I'm parsing the assembly files, but it's just a maintainability issue. So if you have your, that's for the purpose of prototyping, basically, my answer is. So basically, what I do, so when I, make the software engineers write assembly, I can give them the a possibility to write assembly in their favorite editor, and then just parse it and translate it into my embedded DSL. But for me to test it, it's basically simpler to have it as an embedded DSL, because I can, I don't have to write more code than I have to, right? Just write less code. So embedding assembly in Haskell just allows me to write less code, basically.
So it's for your convenience, not
no, it's just an implementation detail, I suppose.
Because I would imagine that if you have like a Spacecraft software that is already there in the assembly files, then you could just parse these files without asking for any modifications. Yeah, that's
true. The point is that there's not that much software already implemented. So it's a really early stage prototype. It's not going to be deployed anytime soon, I suppose. So currently, this company, Ruakspace, still uses the custom hardware approach. Just created this processor, but then they have deployed it, and they will deploy it, I suppose, again. But they haven't still used my verification tool in production. So that's an early stage prototype, and this is my PhD project.
All right, makes sense. Thank you.
Thanks very much. Are there any more questions? Going once, going twice. Okay, fantastic. We get an early break. We've got 20 minutes to break. Thank you again, Georgy. If we could give him another round of applause.
Thank you.
Thank you.